Previously, we had defined actually a context-free language as follows. So if I give you a language L, and there exists a context-free grammar such that the language of that grammar is equal to L, then we would call it context-free, right? It depends on the existence of a context-free grammar. So just want to remind you of kind of a picture we had, but I haven't really technically established it perfectly quite yet. That's what we're going to be addressing here now. Is imagine I have all the possible languages in this box. Pretty profound stuff, right? All the possible languages are in this box. So we have established that there exist languages we called regular languages, right? And we also talked about, now we have this definition of something we called a context-free language. So these are our context-free languages, right? So I drew it like that, but I haven't really established to you that that is in fact the relationship that these two things actually have. So notice that this is actually saying that the regular languages are strictly contained within the context-free languages. Now so far, we've actually learned a little bit of a few little details. First, that we can design context-free grammars for non-regular languages. So what does that mean then? What does that mean then? We can in fact do this. So for example, we're able to come up with a context-free grammar. We also proved that this context-free grammar is correct, that we can actually determine or generate strings of all possible palindromes over a binary alphabet. That we cannot design a DFA for, right? So most certainly it's the case that the context-free languages, there's stuff out here, right? However, it's not quite clear yet that everything in here is in fact inside of this guy right here. There's always technically the possibility that the regular languages could capture other languages that most certainly aren't context-free. So what we need to do, and what we're going to be doing, is we're going to be exploring two things. First, is it in fact the case that the regular languages are strictly contained within the context-free languages? And two, is there a way for me to describe regular languages using grammars, which we have not given any treatment for up to this point? So, for the first one, we're going to sketch out a proof. Now, I'm not going to give you the complete proof, but most certainly I'm going to give you all the bits and pieces to establish this claim. So here's the theorem. So every regular language, L is context-free. So what does this mean? This means that if I give you any one of the regular languages, it's in this here, what I'm saying is they all belong to this. But remember, the consequence of this is that I've already told you that there exist languages that aren't regular, but I can describe them using context-free grammars, which means that they're context-free, right? So meaning that the regular languages are strictly contained within the context-free languages. They're not equal to each other. Meaning that there's always going to be context-free grammars for languages that I could never describe using a DFA, for example. So let me give you a sketch of the proof for this. And I think this one's pretty neat. This will actually lead us to a big thing that's going to come up later on. So you might ask, Dan, how am I going to do this? Well, let's look at our definition up here. It says that L is a language if there exists a context-free grammar such that the language L is, the language of G, the context-free grammar, is equal to L, right? So one way I can go about this is to just present you a context-free grammar, right? So what I'm going to do is I'm going to use the definition of regular, and then I'm going to use the definition of context-free languages, and I'm going to try to take anything that I can call a regular language. I'm going to try to show you how to come up with a context-free grammar, and going to point out the relationship the two things have. So consider Consider any regular language. Any regular language. Language L. But what do we know by definition about L? What do we know about L? By definition, there's several different ways I could describe to you L. So I'm going to use one. Then there is a DFA, a deterministic finite automaton. There is a DFA, D, which has a set of states, set of input symbols, transition function delta, a start state, and a set of final states, which is a subset of those states over there, in the following way. So I'm going to show you, actually, instead of doing it this way, let's do it this way. So there's a DFA D, so that, because what can I say about L then? So what can I say about L? That L is equal to the language of D, right? By definition. So now I'm going to come up with a context-free grammar for L of D. So we're going to construct a context-free grammar, G, which is going to have the for tuple VTPS in the following way. So I'm going to tell you how to construct this context-free grammar. I must stress that this also establishes one direction of a proof that I'm going to present you later. So just pay attention very closely to how this works. And the intuition is going to be fairly simple. Is that, you know, when we have our DFA, right? We read an input symbol, then we transition to potentially another state, right? Well, we have this thing called the transition function. We have delta over here, right? So what if there's a way I could describe these transitions in terms of the productions, the rules that they are? So perhaps I can go from one state to another, and there's a natural relationship between going from one state to another by applying a production rule, and then having productions ahead of a production rule being its state, for example. So let's think about how this works. So for each, so I'm just going to number this. I'll call this state, this 1. For each state, there is a variable. There's a variable and let. So now I'm going to define the set of states as these variables. So V is the set of variables. So I'm going to have PI such that QI is in the set of states. So I'm going to have these variables called PI. For each PI, there is a state QI. So notice the indexing here. Next, I'm going to let the terminals be the input symbols, which in a previous lecture, I gave you this intuition in the past, right? I gave you that idea that the terminals are sort of like input symbols. That's at least a pretty natural way of thinking about this. Now, let's talk about what we do with this transition function delta. So for each transition, delta QIA, right? For each one of the states and input symbols, there's going to exist output for this transition function. That's going to be a state. Suppose it's QJ. What it's going to do is we're going to add a production rule for each one of these. We're going to add a production rule. So which one? Well, think about it. Let's think. Let's think about this carefully. So I gave you this idea that we have the states that are going to each have be ahead of a set of production rules, right? Well, to go from state I to state J, or QI, QJ, it's like if I read a symbol and then I transition to that state, right? But what is that like? Well, it's sort of like the idea that I write down the symbol that I read, Just like if I was walking down the pathway that I take to get to a final state. Because remember, the context-free grammar describes strings that are generated as a result of applying the production rule. So you know, you can think about this like I get to the final state eventually, right? So it's like I'm reading the symbols along the pathway. But what is that like? Well, it's like this. So PI, production symbol, and now imagine this is our input symbol that we're reading. So it's A, and there's actually a variable for state QJ, right? PJ. So for every one of these, you're going to add one of those. Now, next, we got to talk about what about the final states and the start state. So on every final state, something's going to come really nice together here. So for each QI in the set of final states, do you recall how I always like to think about when I put the empty string in? I always like to think about it like it's ending a process. That intuition is going to be natural here. What we're going to do is we're going to include a production rule. PI, production symbol, empty string. So wherever there is a final state, this will allow you to just immediately get to replace that variable with the empty string. Just for free, right? So like I said. So that's rather intuitive, right? And you might say, okay, well, what's the start symbol? The start symbol should have a natural correspondence with the start state, right? And there's only one of those. So it's going to belong to one of these variables here. But which one is it? Well, Q0 was the name of the start state. So there's going to be a variable called P0, right? So the start symbol is going to be S, which equals P0. So this is how I would construct the context-free grammar. You might ask, Dan, what's the relationship between this context-free grammar and the DFA? So one can prove that G generates string W if and only if the following. Well, remember, think about it like this. Like I told you, it's like if I got to the final state. But if I read the whole input, it's going to be just like I was generating each symbol one after the other after I apply each one of the production rules, right? Wow. What does that mean then? If and only if D accepts W. So you could prove this using induction on the length of the string W. And that has a lot to do with the way we constructed this context-free grammar. Do you notice it has a very special form to it? That's not a coincidence. That is not a coincidence. So, that being said, if you carry out and carefully prove this, that's all you need. This ultimately answers the question that every regular language is in fact context-free, right? Every one of those regular languages. They're all strictly contained within there because I already told you that non-regular languages can be described using context-free grammars, right? So it means there's a strict containment. Now you might naturally ask, Dan, how do you describe, because you talk about grammars a lot, right? Well, I gave you a sort of recipe, almost, in this proof for how I could even describe a grammar using an idea of a DFA, right? So I showed you how you can construct a context-free grammar, but perhaps it entertains this idea that what if we could talk about grammars within the context of regular languages? So how can I do that then? Because we haven't given any treatment to that yet. And we're going to be fairly, I think it's pretty surprising at first. But once you understand this proof, this is actually one direction of this claim. is that we can actually define grammars for regular languages too, just specifically them, called regular grammars. So I'm going to define these. I'm going to give you an example, and I'll give you the connection that there exists. So what you might ask is, Dan, what is a regular grammar? A regular grammar is a special kind of context-free grammar. So it's a special case of a context-free grammar. And we're going to focus in on what are called right regular grammars, or some people call them right linear grammars. So just for the sake of brevity, I'll call them right regular grammars. That right is looking really excited here. So how do you define this? It's defined with a for tuple. There's no period here. No period. G, it's going to be a for tuple like we usually have. VTPS. Where variables A and B are among the set of variables. And we're going to also have X, which is going to be one of T star. Remember, T is a set of terminals, but it's T star. So that means also you get the empty string. And all production rules are of the form so you have a variable, you have 0 or more terminals, then another variable. I must stress, remember, these don't have to be distinct. It's just another name for a variable. Or it has to be that from a variable you just get terminals, or the empty string. So these are what we call right regular grammars. Now you might ask, what does that mean? So I'm going to give you an example in a moment, but there's also another concept called a left regular grammar or left linear grammar, which is simply defined in the exact same way, except you just switched around these two. So it would be BX instead of XB. So both of those, so left regular and right regular, are called regular grammar. So either one is a different form of what we call regular grammar. So let's consider an example. That way we could see that this thing actually describes something interesting. So I'm going to define a grammar called G even. It's going to have two variables, A0, A1. It's going to have terminals 0 and 1, so it's over the binary alphabet. P, and the start symbol is going to be A0. With production rules as follows. So I'm going to write out the grammar first, then we're going to think about what the language of the grammar is. So I want to convince you that this is in fact a regular grammar. In particular, it's a right regular grammar. So remember, I'm only allowed to put 0 or more terminals, then a variable, or just a bunch of terminals or the empty string. So I'm going to have 0, A1, so that's of the form. I'm going to have 1, A0, that's still of the form, right? This is a terminal, that's a variable. We're going to have the empty string, that's of the second form right here. Then we're going to have A1. A1 is going to be 0, A0. That's again of the form in question. And I must stress, remember, it can have more terminals that come before the variable here. That's why it's T star, not just T. Among the reasons why we also need the empty string. Remember, T0 also includes that. So I have 1, A1. So I want you to think about what the language of this grammar is. So indeed, this is actually a context-free grammar, but it has a much more specialized form. So I'll give you a bit of a tip of how this works. So you start off with A0, right? Now, if you consider, you have three different options here. You can take the epsilon, you can stay in A0 by including a 1, or you can just simply take the 0 and then have to consider A1, which gives you the option of putting another 0 in, which gets you back to A0, or it stays in A1 when you read a 1. So notice that on 1s, it stays, it has the exact same variable. However, whenever it's a 0, it swaps to the other variable. So this should remind you of something quite vaguely remind you of something. If it helps, think about it as a DFA and think back to how we worked with this proof over here. So if you think of the proof over there, you imagine you have two states. On 1s, it stays in the same state. On 0s, it swaps to the other state. Which one here, if you think about that proof over there, which one is the final state then? There's only one of them here, right? Which one is it? It's this one. So this would correspond to the final state, because it has this production rule right here. That's at least one way you can think about it. So what's the language of this grammar then? Well, certainly you cannot finish with a terminal string when you have A1 present, right? So the language of G even, I sort of gave you a hint with the name. It's going to be the set of all binary strings such that W has an even number of what? Even number of what? Well, notice that if I go to A1, it requires me to read a 0 or produce a 0, and I require another 0 to get back to A0, right? So it's akin to one of our examples where every time I put in a 0, I have to take another 0. So I have to walk through almost like it's a cycle. That's not a coincidence, by the way, because it is a cycle if you think about this in terms of its corresponding DFA, right? It's going to always have to be that it generates an even number of zeros within that binary string, right? We don't care about the ones, right? The ones don't matter in this process. So we actually know how to generate a DFA. And you could use that proof over there to help you, but most certainly we've studied DFAs that look just like, that do describe languages just like this one. So we won't prove this. We won't prove this. However, what we could do is we could actually come up with a much more broader characterization for a regular grammar. So here's a theorem. I'm not going to prove it. I've actually given you some of the pieces for proving this claim. There's actually a couple of moving parts here. The first one is that I talked about also this notion of a left regular grammar. You can actually show that the left linear grammars also describe the same kinds of languages. In fact, the way the proof works is that you actually talk about the reversal of the language, which we've already established in a previous lecture that that's regular too. That describes regular languages as well, right? Another moving part is the fact that once you have this idea that right regular and left regular describe regular languages, it doesn't really matter if you talk about right regular or left regular. It's more of a convenience at that stage, right? So usually people stick with one or the other when they do this. So just as a reminder, remember a regular grammar, they might be talking about a right regular, right linear grammar, or they might be talking about a left regular grammar. It doesn't matter. Just be specific when you're doing it, okay? But here's the theorem. So a language L is regular if and only if, so this is a strong statement, if and only if there exists a regular grammar G so that L is equal to L of G. So if you're staring at this and like, okay, so how do we go about this? Well, I'll give you a hint on one of the directions of the proof. Well, notice that over there, I've shown you how to construct a context-free grammar. Look carefully at the form of that grammar. And you'll notice very quickly that it's actually what kind of grammar? It's a regular grammar, right? It's a regular grammar. So it's a regular grammar. Naturally, once you do that, you've shown me, okay, well, whenever I give you a regular language, which has a DFA, right? I can give you a way to come up with a regular grammar. The other step in this is just simply coming up with a regular grammar and showing you how to come up with automaton, probably, right? Once you get a hook into this, it's not too terribly scary. But the point I'm getting at is that this relationship exists. So if I come up with regular grammars, that's just another way of describing regular languages, just like regular expressions, just like finite automata. So this relationship actually exists. You might ask, Dan, you talked about this idea of right regular or right linear and left regular or left linear. What happens if you allow there to be production rules which are both the ones that obey the right regular grammars and the left regular grammars? That means that we'd also allow it where the productions also have this form. So we allow both of these forms at the same time. You might ask, Dan, does this also give us the versatility of describing regular languages? And the answer is no. Most certainly you can. If I give you a regular language, yes, most certainly you can describe it using such a grammar. But also, if I give you one of these grammars, most certainly this is context-free, right? But here's the big but. Once I introduce this into this definition over here, we end up with something else. We end up getting what is called a linear grammar. Now, linear grammars actually describe things called linear languages. You might ask, Dan, where does it get that name? Well, look quite carefully at how it produces terminal strings, and you'll get your answer very quickly. So this is an example of a linear language. Now, I'm not going to prove this here, but all languages described by linear grammars are context-free, but the opposite isn't true. So it means that this is just another set of languages that's kind of sandwiched in between the regular ones and the context-free ones. So that's not really the focus, but I thought I would mention that's a fun little aside. So indeed, we've established that if I give you the regular languages, they're indeed strictly contained in the context-free languages. And we can also describe regular languages using grammars, namely regular grammars.